All right, this is AP Chemistry Notes, page 38 to 40. So we start with what's happening when we do dilutions. Of course, as you dilute something, the molarity, or any concentration for that matter, must go down. And the formal definition is that molarity of concentrated times liters of concentrated equals molarity diluted times liters of diluted. Now, the reason this one is in liters is because molarity times liters equals moles. And essentially what the math is saying is that the moles of solute before the reaction is equal to the moles of solute after, and that makes sense. If you put a certain amount of salt into water, if you dilute it, the only thing you're adding is water. So the moles of salt isn't changing. You're not adding or removing salt. And that's what this equation is showing mathematically, is your moles before and your moles after of solute is the same. You're just adding, in my case, water. Now, because the molarity is defined as per liter, that's why this has liters, but you can cheat if you want to. I prefer this version, M1V1 equals M2V2. So in other words, your volume can be in milliliters as long as they both are. And it works out mathematically because you're technically 1,000 times off on the left, but you're also 1,000 times off on the right, so it cancels. So you're fine to use any volume you want, but they better match. So we typically do milliliters. So take this first problem. Calculate how much 12.1 molarity HCl is needed to make 500 milliliters of a 0.75 molarity solution. Now, like I mentioned, I do this a lot. This is one of the most common calculations myself and other chemistry teachers do, because we don't typically store the acids diluted. To store the acids diluted, and other chemicals for that matter, it would take up way too much space. So we store them concentrated, and hydrochloric acid concentrated is 12.1. And then we just dilute it as needed. And so let's just say that I needed 500 milliliters of 0.75 for a lab that I'm setting up for the class. What I need to solve for is how much of the concentrated do I need? So my question is V1. You just plug the numbers in, pretty straightforward, and you get a V1 of 31 milliliters. Now, a way I like for you to present your answer is to not just say 31 milliliters, because it would be 31 milliliters of what? Is that 31 milliliters of water? Is it 31 milliliters of 12.1 molar? Is it 31 milliliters of 0.75 that you end up with? So try to be clear, 31 milliliters of 12.1 molar HCl. And V1 is enough to say that that's what you need to start with. And so if you actually were to make this, what you would do is you would measure this out and dilute it with water until you get to 500 milliliters. So that brings up an interesting thing. When making solutions, you don't add 500 milliliters. If you add 500 milliliters, you would now have 531 milliliters, and your concentration would be wrong. You add solvent until you reach the desired volume. So this is add water until you reach 500. That's an important detail. And in this case, when you dilute concentrated acids, there's some safety things involved, but that's not the point right now. So if somebody's thinking, well, you wouldn't really want to pour the water into the acid, they are correct, but I'm not talking about how to actually do this right now. We'll discuss how to dilute acids safely in another lesson. All right, it does say how many milliliters of water must be added. And my point here is that it's not 500. So it's 500 that we want. So if we're going to have 31 milliliters of the concentrated acid, you would end up doing 469. And it's just important that you realize that you don't add 500 milliliters. Right, solubility. There's a couple different things this word could mean. It could refer to whether something is dissolving, and then it could also refer to how much of something is dissolving if it does. So with the first one, whether, that's where we like to use the phrase here, the like phrase. Like dissolves like. Things dissolve in similar things, with the biggest thing being polarity. So polar things dissolve in polar things. So like it mentions here, alcohols and sugars dissolve in water because everything here is polar. Organic things like oil don't dissolve in water because a lot of them are nonpolar. Now, there are many organic things that do, but it's kind of a general phrase that a lot of organic stuff does not dissolve in water because it's nonpolar. There's more to whether things dissolve in each other than just polarity, but polarity is the kind of the starting point. You could also look at other attributes like bonding and how similar their other intermolecular forces are if they're relevant. And we'll get into more details about that as we go through this section. Okay, now on to how much something dissolves. Well, the first thing to look at is temperature. If you increase temperature, you're helping whatever is endothermic. So if the thing dissolving is an endothermic process, you help it. And that would be the case with solids. Solids generally, not always, but generally, that is an endothermic process. So heating it helps, like dissolving salt or sugar into water. Gases, however, when you want to dissolve a gas into a liquid, you need to calm the gas down. You need to slow it down. And so you don't want to give it too much energy. And an example would be, let's say you had 2 cans of soda. One's in the fridge, one's at room temperature. If you open both cans and come back to them after a minute or two, you'd probably find that the one that was colder has kept its carbonation better because the dissolved carbon dioxide has been able to remain dissolved better than the warm one. So here's an example. Which of the following will help solubility? Now I have to say, this word is incorrect. I don't like this word reactions right here. A reaction should refer to something that's changing its identity. These things are not really changing their identity. A better word right here would be which of the following processes. Because dissolving salt into water is not a reaction, at least not to me. So here, the first one is sugar. That's a solid. So unless we know otherwise, that's going to be yes, heating will help. Second one's a gas, so no. Third one's a solid, so yes. And the last one is my example with soda. That's a no. Now, before we move to the next page, I have a note here. This phrase, like dissolves like, means that similar things dissolve in similar things. Well, here is a bit of a conundrum. Oxygen is nonpolar. It's this. That's nonpolar. But it dissolves in water, which is, of course, polar. My question is, how is it that this dissolves in polar solvents like water? And I want you to see if you can figure it out on your own before we talk about it. So I mentioned that I added it to the homework. All right, we were talking about how temperature affects how much something dissolves. Now we're going to look at pressure. When it comes to pressure, it mainly refers to gases dissolving in liquids. And what you want to do is you want to increase the pressure. That'll help push the gas into the solution. And so going back to our carbonated beverages, they're usually made at 4 atmospheres to help get a lot of CO2 dissolved. Of course, when you open it, you now release the pressure and you let it go to 1 atmosphere, which is why the CO2 starts leaving and it becomes flat over time. Now, this brings up something I experienced once. I was at a get together, and on the table where all the food and drinks were, they had some 2-liter soda bottles. And I don't know, maybe a half hour to an hour into the get together, I noticed some of the soda bottles had been squeezed. So imagine emptying half the liquid of the soda bottle out, and then before tightening the cap, squeezing the center of the bottle and squeezing most of the air out, and then capping it so that it, when sitting on the table, has this big dent in the side. So at first, I just thought it was a random act. I figured somebody was maybe holding the bottle and holding the cup, and as they were pouring, they had to grip the bottle really tight and squeeze it. So I just ignored it. But later on, I noticed all the bottles started to look like that. Somebody was intentionally squeezing the air out and capping it. And so I kind of predicted why they were doing it. So I asked them, I said, why are you doing that? And they said it keeps it more carbonated. And I didn't want to be rude and tell them that they were flat out wrong and what they were doing was making it worse. So I didn't say anything. I just kind of went, oh, okay, and didn't correct them. But it turns out they were flat out backwards. What they were doing was making the soda go flat faster. And so I want you to think about it, and we'll talk about it in class. I'll also show you the Fizz Keeper. It's a corny little device that actually helps if you're willing to take the time to do it. Okay, next thing, Henry's Law, named after a English chemist. And it's pretty much a simple equation that just relates concentration and pressure when gases are being dissolved. It pretty much is just saying that there's a direct relationship between pressure and the concentration of a gas. And there's going to be a constant that allows the concentration and pressure to talk to each other. Sometimes I've seen the constant on the right, and sometimes I've seen it on the left. So just pay attention to the units, and that will tell you which version you have. So include your units in the calculation, and that'll tell you if you have the wrong version. Your units won't make sense. There's an example. Pure oxygen, 1 atmosphere, 20 degrees, so fairly normal, makes a solution of dissolved O2 at this, 1.38 times 10 to the negative 3. Calculate the concentration of dissolved O2 when the temperature is still 20, but the pressure has been lowered. Okay, the first thing I'm going to do is solve for K based on the initial data. So initially, they said this molarity, this pressure, and I'm using the version that has K on the right, but you can use the other version. That gives me a constant of 1.38 times 10 to the negative 3 molarity per atmosphere. I then use the same equation to solve for the new concentration, same constant, new pressure, and we get, of course, a lower concentration because there's less pressure pushing the gas into the solution. And the last thing for this lesson is the solubility graph. It's a graph that shows how soluble things are or how much they will dissolve per 100 milliliters of water. It's important to realize the graph is per 100 milliliters of water. I'm sure that there are other versions that are different amounts, but this is a pretty convenient amount to start with because 100 milliliters of water is a significant amount and 100 is easy to work with. So let's take a look at it. I have it over here. This particular graph has 4 solvents: sodium chloride, calcium chloride, sodium nitrate, and potassium nitrate. Notice that every one of them increases solubility. Solubility is here on the y-axis. Notice solubility goes up for all of them as temperature increases, which is what we would expect from solids. There are exceptions, but this is the typical case. If it was a gas, we would expect the opposite. So if we were trying to dissolve a gas, we would expect this curve, something like that. All right, you can see that certain substances are very sensitive. So you can see sodium chloride is not sensitive. It really doesn't change based on temperature very much. It does go up a little, whereas potassium nitrate is very sensitive to the temperature of the water. Some things to be aware of are my three assumptions. I've already mentioned 100 milliliters or 100 grams of water. The line, if you're on the line, you are right at saturated. So the line represents the saturated solution. Above the line would be either impossible or supersaturated. And for these problems, you kind of want to ignore the supersaturated concept unless they say to use it. And we assume that water is the solvent for this particular graph. So if we take a look at a problem, first one, how much potassium nitrate will dissolve in 35 milliliters of water, 30 degrees. So you just go over here on the graph. See if I can get them both on the screen at the same time. I can. And so potassium nitrate is that really steep curve. And it says 30 degrees. 30 degrees, potassium nitrate is right about here. So where I made this mark right there, that is how much potassium nitrate you can dissolve in 100 milliliters of water. And I estimated it to be right about 44. So this is my conversion, is that in 100 milliliters or 100 grams, you get 44 grams potassium nitrate, but we don't have 100 grams of water. We have 35 grams or 35 milliliters. So you just use this as a conversion factor. Some people like to do it this way, where they just do a proportion. That's fine. I just like to do it a conversion factor like a mole problem. And you get 15 grams, which makes sense. We've got less water than the chart says. And here's another one. How much water at 55 is needed to dissolve 25 grams of calcium chloride? So again, start with what you're given and then find calcium chloride 55 degrees. That is here. And I estimated that to be about 107. And notice in this case, because I'm going away from calcium chloride, I put that on the bottom. I want the solvent water, and I get 23.4 grams or milliliters for that matter. Based on the prior problem, let's say we do this. And let's say that we actually get this exact solution where we have 23.4 grams of water and 25 grams of calcium chloride. So in other words, we have a saturated solution where it's right at its full limit. Let's cool it. Well, if we cool it down to 10 degrees, it can't hold all that calcium chloride anymore. And the question says, how much solidifies out? So what we need to do is figure out how much can be dissolved at 10 degrees and the rest will solidify. So I know the amount of water from my prior answer. This is my new conversion based on 10 degrees. So 10 degrees, calcium chloride is here. It's right at 80. That gives me 18.7. Now realize that's how much will stay dissolved. I subtract that from the starting amount to say 6.3 grams will solidify out, or some people like to say precipitate. All right. Anything we need to talk about in the homework? You'll see I added that question about how is it that O2 dissolves in water. The only one I really want to talk about is I added a review question. If something has a negative delta H, if we want to dissolve as much as possible, what do we want to do with temperature? In this case, we'd want to cool it. So a negative delta H means that the process is giving off heat. So we don't want to put heat into it. That will make it harder. So in this case, you'd actually want to cool this particular one. And that should do it for these 3 pages.